In this video, we're going to be evaluating integral of minus infinity to infinity of z squared over z squared plus 1 all raised to the power of 2 into z squared plus 2z plus 2 dz. And you have to evaluate that this is equal to 7 pi over 50. This is equal to 7 pi over 50. So this is an example under calculation of definite integrals of residue calculation of definite integrals. So we're going to be jumping right into this. So first of all, let's consider the denominators. We have z squared plus 1 all squared into z squared plus 2z plus 2. Let's equate it to be 0. Let's equate the denominator to be 0. That means z squared plus 1, which is this one, will be equal to 0, and this means z squared will be equal to minus 1 and z will be equal to square root of minus 1, so z will be equal to plus or minus I. Remember, square root of minus 1 is I. So at this side now we have z squared plus 2z plus 2 to be equal to 0. So here we have a to be 1, we have b to be 2 and c to be 2. Using the quadratic formula, we have z to be equal to minus b plus or minus b squared minus 4ac divided by 2a. So here we have z to be equal to minus 2 plus or minus square root of b squared, that is 4 minus 4 into a, which is 1, and c, which is 2, divided by 2 multiplying 1. So z here is equal to minus 2 plus or minus square root of minus 4 divided by 2, and this is minus 2 plus or minus 2i. Square root of minus 4 is 2i, and this is going to give you 2. Square root of minus 4 is equal to square root of 4 times square root of minus 1, which is I 2. So we have 2i. So here now this will now simplify. So from here we are going to have minus 1 plus or minus I, because the factorized 2 outside 2 will cancel 2, and you have minus 1 plus or minus I. So this is what we have. These are the two roots of this quadratic equation. So let's look back to our question here and see how we can substitute this. So we are going to be using this as our various poles. So first of all, we are going to be looking at z to be equal to I, that is the pole I, and we'll be taking the order here, which is k, to be equal to 2. So we have our pole here to be z equal to I and our order to be 2. So let's substitute this into the formula, the residue formula, which is this, equal to limit as z. Okay, let me write out the formula first of all. Limit as z turns to a of 1 all over k minus 1 factorial of the k minus 1 divided by the z k minus 1 into z minus a raised to the power of k multiplying f of z. So this is the residue formula. So substituting this now, we're going to have limit as z tends to I, because a here is I, 1 all over k is 2 minus 1 factorial, then we have the 2 minus 1 over the z 2 minus 1. So we have z minus I squared multiplying f of z here, which is z squared divided by z plus 1 squared into z squared plus 2z plus 2. So let's simplify this further. We're going to have this to be limit as z tends to I of 1 over, of course this is 1, so we're going to have dz into z minus I squared dz divided by, so look at this now, z plus 1, let me use a different ink, z plus 1, z squared plus 1 is equal to z plus I into z minus I. So that means z squared plus 1 squared will be equal to z plus I squared into z minus I squared. So we are now going to write this as z minus I squared into z plus I squared into z squared plus 2z plus 2. So that means this we divide this, then we're left with a minus 1 into limit as z turns to I of d dz into z squared divided by z plus I all squared z squared plus 2z plus 2. So we'll be moving to the next slide to expand this. So let's expand this. This will be limit as z turns to I into, we are going to be differentiating this using the quotient rule. So it means we are going to keep the denominator, differentiate the numerator, minus keep the numerator and differentiate the denominator. So if we do that, if we keep the numerator to differentiate denominator, we are going to have z plus I squared into z squared plus 2z plus 2 into 2z, and this is minus now. You now keep the numerator and differentiate denominator, should be z squared into differentiating this. Now differentiating the denominator, now we are going to be using the product rule, which means we differentiate this, we have 2 into z plus I into, keep this, z squared plus 2z plus 2, then this is plus, now keep this and differentiate this, we are going to have 2z plus 2 into z plus I all squared, and this is divided by z plus I squared z squared plus 2z plus 2 all squared. So let's rewrite some things here. We have limit as z turns to I into, we have 2z into z plus I squared into z squared plus 2z plus 2, and we have minus z squared into 2 into z plus I into z squared plus 2z plus 2, then we have minus z squared into 2z plus 2 into z plus I all squared, and this is divided by z plus I squared z squared plus 2z plus 2 all squared. So from here we are going to do the substitution right away, and if we do that here, we are going to have 2I into 2I squared into I squared plus 2i plus 2, then this is minus I squared into 2 into 2i, and this is multiplying I squared plus 2i plus 2 minus I squared into 2i plus 2 into I plus I squared, or divide by I plus I squared into I squared plus 2i plus 2. This is all squared then. So we are going to, this implies that we have 2i into minus 4 into 2i plus 1, then this will be plus, we have 4i here into 2i plus 1, and this is plus 1 also, which there's no need to write the 1, and this is 2i plus 2 into minus 4, or divide by 2i squared into 2i plus 1 all squared. So let's evaluate this further. We are going to have minus 8i into 2i plus 1 plus, here we are going to have, so here we have minus 8 plus 4i here, and this is plus minus 8i minus 8 here, and all of this, and all of this is dividing 16 into 2i plus 1 squared. So let's move this here and solve. So from here, looking at this, we are going to have 16 minus 8i minus 8 plus 4i here, minus 8i minus 8, all divided by 16 into 2i plus 1 squared. So let's look at our numerator. We have minus 8 plus 16, then this is going to give us minus 12, minus 12i divided by 16 into 2i plus 1 squared. So this is minus 12i divided by 16. So let's look at this now. We have 2i plus 1 squared, 2i plus 1, 2i plus 1. If we do this, we are going to have 4i minus 3. If we expand this, we have 4i minus 3. So this is going to be 16 into 4i minus 3. And then a minus 1, I remember this a minus 1, will be equal to minus 12i divided by 16 into 4i minus 3. So from here, let's simplify this. We are going to have 4 can divide 12 here. We are going to have 3i divided by 4 into 4i minus 3. So this will be minus 3i divided by 16i minus 12. So this is what we have. So at this point now, we are going to rationalize the denominator. That means we are going to have a minus 1 to be equal to minus 3i divided by 16i minus 12 times 16i plus 12 divided by 16i plus 12. So this is going to be equal to, I would like you to do that on your own. This is going to be equal to 48 minus 36i divided by 16i plus 12 all squared. 069 minus 12 all squared. So if you finish this up, you are going to have your answer to be 9i minus 12 divided by 100, and this is your equation star. So we are going to be doing for b minus 1. So for the second one now, b minus 1 to be equal to limit as z turns to minus 1 plus I of 1 all over k. Here is 1 now, 1 minus 1 factorial, and this is the minus 1 minus 1, and the z is of 1 minus 1 of z minus 1 plus I. Then this is f of z here, which is what? Z square divided by z square plus 1 square into z square plus 2z plus 2. So this is b minus 1 limit as z tends to minus 1 plus I. Then this is 1, this is 1. You are going to be left with 0 factorial is 1, and this is the 0 over the z. Anything raised above 0 is 1. So we'll be left with z plus 1 minus I multiplying z square divided by z square plus 1 square all square. Now let's look at this. We can split this. We're going to be having z minus 1 minus I into z plus 1 minus I. Sorry, this is plus here and this is plus here, because if you, all right, let's work this out. If we do this z plus 1 plus I multiplying z plus 1 minus I, this is going to give you z squared plus 2z plus 2. So this is equal to this, so you can replace it here. So now that means this will divide this one here. So this will become b minus 1 to be limit as z tends to minus 1 plus I into z squared divided by z squared plus 1 all squared into z plus 1 plus I. So substituting now the limit, taking the limit, we are going to have minus 1 plus I all squared divided by minus 1 plus I squared plus 1 here all squared multiplying minus 1 plus 1 plus I minus 1 plus I plus I plus 1. So now let's consider this minus 1, change the ink. Let's consider minus 1 plus I multiply minus 1 plus I. This is going to be equal to minus 2I. So that means this is going to reduce to b minus 1 will be equal to minus 2I divided by minus 2I plus 1 all squared into minus 1 plus I plus 1, which is minus 2I divided by minus 2I plus 1 all squared into this. Cancel this, you have 2I remaining here. So b minus 1 will be equal to minus 2I divided by 2I into 1 minus 2I. So let's look at this. This can divide this. We have minus 1 all over 1 minus 2i. This is squared there and this is squared there. If we solve this, say you multiply 1 minus 2i into 1 minus 2i, you are going to have minus 4i minus 3. So that means this is equal to minus 1 divided by minus 4i minus 3. So the same process you can rationalize the denominator. This is minus 1 all over minus 4i minus 3 times minus 4i plus 3 divided by minus 4i plus 3. And if we do this, your answer is going to be 3 minus 4i divided by 25. So, and let's call this equation star star. So we are going to be making use of equation star and equation star star to find our final answer. So these are equation star and these are equation star star. We are going to be making use of the two equations to find our final answer, which is from the formula of the residue calculation, which says integral of the curve C of f of z, the z is equal to 2 pi I into sum of residues, and these are residues. So this is apparently going to be f of z, the z, to be equal to 2 pi I into a minus 1 plus b minus 1. So we are going to have that to be f of z, the z, to be equal to 2 pi I into, then here we have 9i minus 12 divided by 100, then this is plus, and here we have 3 minus 4i divided by 25. So that means we're going to have 2 pi I to be into, the LCM here is 100, and we have 9i minus 12, then this is 25 will go into 100, we have 4 times rather, then 4 times 12 times 3 we are going to have 12, then this minus 4 times 4 we are going to have 16i, and this is going to be equal to 2 pi I into minus 9 minus 9i remember this is plus here, this plus here, so minus 12, sorry, this is plus here, so minus 12 plus 12 we go to 0, then 9i minus 16i will give us minus 7i divided by 100, and from here you discover that I times I here will give you minus, then affecting this minus, and also 2 we divide 150 times, so we are going to have 7 pi over 50. So this is to show that integral of minus infinity to infinity of z squared divided by z squared plus 1 all squared into z squared plus 2z plus 2, the z is equal to 7 pi over 50, and this is the solution. Please like this video, subscribe to this YouTube channel, and don't forget to hit the notification bell to get notified each time we upload a video. Thank you.